to make a forecast or not, that might be a different thing, but think broadly about it. You know, think about what you might predict or forecast, or how you might use it in your capstone. You know, anytime you've got a trend, this kind of stuff's going to let you predict a trend. And so, you know, the trend might not necessarily be sales, right? It could be anything. But these techniques that we'll cover, simple naive approach where it's just the last value. We'll approach weighted average. We'll do this exponential smoothing. We'll even talk about linear regression, and I won't go into details on that because that comes up later on in statistics and other classes. But we'll talk about it, and you'll get an Excel to show you how to use it if you want. And all these techniques are easy to use, and you can think about them broadly. In fact, when I get to the average part, I'll mention some broader context. So I think you'll like this. I think you'll like this chapter. I think you'll like these techniques. The set of view graphs are really good this time. I won't make fun of them. And I've got Excel examples for things. And then I went ahead and posted almost all the solutions to all the problems, even though I'm not going to go through them all, except for the two that are homework. I cut them out. But if you need to look at them, you know, then you got all their examples for every one of them. Like I said, I won't go through them all, but you got them all if you want them. And so anyway, I think this is really good chapter. And I think you'll like this material and find it applicable and not that daunting. So with that introduction, let's talk about forecasting. This is fun stuff, I believe. So we're gonna look at all the pieces of forecasting, and the goal here is, you know, demand and supply and price type forecasts. But again, you can be anything, and so keep the broad perspective in mind. And we're going to talk about the 4 laws of forecasting. That's just motherhood and apple pie stuff, which is amusing, but you'll like it. And then we're going to divide forecasting into two big blobs, qualitative and quantitative. And almost the entire bulk of the chapter is quantitative, which is good, because I feel like a lot of times the qualitative is, you know, the hand waving type stuff anyhow. And so I'll mention it. And they hardly, the book mentions it even more than the view graphs, but I'll mention a little bit just because you may wind up seeing yourself in that sort of place. So yeah, from the quantitative, we'll do time series, moving average, linear regression. We'll also talk about causal forecasting and linear regression, multiple regression. I've got you a nice example on how to do that. And we won't talk about the statistics relative to it because that's next class, but you'll have them. And then they'll make more sense to you when you get to that class. And then they mentioned computer-based forecasting, just one view graph. So I've got a little lunchtime thing to talk about on that. And then let's see, and that's defined, that's all it is. Okay, so we know what a forecast is, right? We all think of that word. You know, we always think about weather. That's a whole different thing. But you know, you want to use forecasting to determine whatever it might be. Your demand, if you're a company, your capacity needs, right? Your business plan, any kind of things related to what your business is going to be in the future. And so you can see how you're going to have forecasting if you run a business, so you know how to expand, what to buy, what to plan for, anything. So that's the whole focus of this chapter. What are ways to do this given your past data? And so you could do demand, you could do supply, you could do price, and you think about it like one of the examples they give, the case study. Yeah, the case study talks about one of the questions is, when should we expand our production capability? So they're using the forecast to look ahead in the future year to say, when is our production reaching a certain level, and then we need to expand to meet that level. And so, you know, yeah, then you could tie it to your supply, you could tie it with your supply chain and whatever. So you can see a little bit of the motivation for what's going on. All right, so here's the laws, which, like I said, are just amusing and motherhood and apple pie type stuff, but they're always wrong. Well, of course, they're forecasts. They're predicting the future. Who can predict the future? Near term's better than far term. Yeah, that's obvious too, right? The further out you get, the worse they are. In fact, far enough out, they're not even relevant, you know. And think about all how business has changed in a decade. And so you know, you got to think about that. If you can group your products together, that seems to be more accurate. I think that's obvious too, from the sense that you know, if you've got variation in one product and variation in another, when you're adding them together, it kind of tends to help smooth that signal to noise ratio out. You got larger signal. And one of the examples they give, I think they gave it in this book. I read so many things, sometimes I don't know what's in it. They talk about the demand for green cars. I can't remember if it's this chapter or not. But anyway, so, if you were trying to predict the demand for green cars, you'd have a lot more error than you would if you just try to predict the demand for all cars of that make and model. I was like, yeah, that makes a lot of sense. And then, there are no substitute for actual real values from your, from data. And they did give an example about that. If you know data and you're just not using it correct, what they mean by calculated values is, don't try to forecast something that you could calculate from your known sets of data. Gosh, that makes a lot more sense. Don't predict something that you could measure or determine some other way. All right, so like I said, they're going to break the forecasting up into two broad categories: qualitative and quantitative. And you can obviously see the difference. Of course, qualitative you would use when you don't have enough data, and you're going to come up with expert opinions, guesses, panel things, the Delphi approach, these sort of stuff. And then quantitative is what you do when you have real data, and the data might be time data, or it might be a causal model. By the causal model, they mean you're not relating your forecast to time necessarily. Like the example they give, and we'll cover in the view graphs, they're relating home sales to mortgage interest rates. Yeah. It doesn't have to be a function of time. It could be a function of a number of things as well as time. And so with the linear regression and the multiple regression, we'll also show how it doesn't have to be a linear function. We're often thinking of it that way. No. It could be, a quadratic, a cubic, an odd function, any kind of thing. And I'll show you how to handle that. And it can be a sum of different functions. One of the tools that I'll give you here to evaluate these methods has a constant term and a trend and a periodic term and some noise. And so, it could have all these things. And so quantitative is when you got the data and functionality is assumed or so this nice small figure is splitting them up that way in a diagram. So they've got qualitative on this side, and they're listing things like market surveys or panel consensus, the Delphi method. Quantitative over here, and they're splitting them up into time series and causal. In the time series, we'll do weighted average, moving averages, exponential smoothing, linear regression, and multiple regression shows up over here. Because you could use linear regression for time. The variable could be time as well as mortgage rates or, color of car or whatever. So let me, at this point, because I don't think, no, it's probably, I can do it on the next slide. Okay. So here's the qualitative list, market surveys, a consensus, Delphi method, life cycle analogy, or build-up forecast. But let me say something about the Delphi method, because I thought it was interesting. The book talked about it. That's sort of where you get some experts, but rather than bring the experts together in a room and have them all argue with each other, the primary approach with the Delphi method is you let them be independent and not communicate with one another. So you ask, expert A, B, and C, and D to provide their estimate for your forecast, whatever it is, price, demand, whatever, and their justification and reasoning. And then you collect it together and decipher it, distill it, come up with some salient points out of it, and then you send it back to them, still independent. So, you would send it back to them and say, hey, did you consider these things? Or did you think about this, variation or this thing coming in the future? So they've all been given a new, the additional set of information that's been distilled and updated based on their initial input. And you do that 2 or 3 iterations, however many it takes, until you come up with basically a consensus from all the experts. And then you could probably think, well, I've got these multiple experts that now, given all the information that they've all had shared without, arguing with each other, they've come to a sort of an agreement. It doesn't have to be exact agreement, but a general agreement on what the future system or business situation or whatever looks like. I think of all the qualitative methods that might work the best. Of course, it's going to depend on the experts you choose and how well they are acquainted with your business and that sort of thing. But that's sort of the idea too. You're hoping with this feedback thing as well. If I get 2 of them that are great and 3 of them that are only so-so, well, at least if I bring the information together, pile it back up, send it back out, I'm re-educating the 3 so-sos, And maybe if they're hard workers, they'll go out and, follow up some of those, oh, I never thought of that type leads, and they'll improve their estimate. So that's probably about all they're going to say, as I recall, about qualitative, which is okay. All right, so now we'll switch into quantitative, and the first approach that they'll talk about, first broad set of approaches, I should say, is time series, which of course makes sense. That's probably the most intuitive and clear from the forecasting perspective that you can think of, right? I got demand or price or something as a function of time, and I want to predict it. All right, so yeah, I've got a scatter plot here, right? Number of patients, yeah, as a function of week. All right. And so let's see. Let's look here. We got a graph. So some of the patterns that you see in a time series that you might want to worry about relative to what forecasting method you're going to use or what parameters you're going to pick in the particular method you use are, things like randomness, aware of that, random noise, that's always in there. A trend, whether it's trending upwards or trending downwards, basically the linear portion. And then seasonality, repeated pattern, the periodicity. So, these are the things you think about any signal, right? It's got noise, it's got, a linear portion, it's got a periodic portion, and it might have multiple periods, which I didn't actually build that into my little model tool. I probably should have. That would have been fun, have 2 or 3 different periods. And when you do these things, and this is part of the reason I supplied you with the little tool, which I'll show you in another couple of view graphs, after we get through the other time series methods. When I encounter something like this that I want to use, whether it's a time series predictor or exponential smoothing, and I'm really going to use it at work, not just to slap together and quickly do a homework problem, I always build myself a test, a test case, a fake set of data, and a fake set of data that I know very well, and then I can manipulate, and then you can play with it, because it is important to understand how, especially when it comes to prediction or statistical things, as opposed to, algebra where I'm going to solve x squared plus y equals z or something. Those are going to have a definitive answer. But when I'm coming up with these kind of techniques that are, have error or statistical uncertainty in them, it's important to understand how different things like randomness or a trend or periodicity affects your using these. Because, if it's highly sensitive to randomness and you're applying it on a set of data that's highly random, your answers may be crappy. And you want to kind of bound this and understand it. And plus, when you're using things like linear regression or something straight out of Excel, you also want to understand what something like the R-squared is, or the p-value, or the t-statistic is. Because, they're telling you something, they're stuck in there for a reason, and if you ignore them, well, you may be okay, because you may have luckily picked the correct data set and the correct approach and the correct parameters, but you may not. You may make some really glaring mistakes. And so, again, if you can build a little test tool, play with it and manipulate it, something that doesn't take very long, and then, oh man, I understand it. Randomness affects it here, or if I have high periodicity, I want to use this technique, or I can't use this technique when I got a trend unless I do X, Y, Z. You'll learn a lot, and playing with it will give you, it's experiments with the software. And so anyway, these are some of the trends you can have. All right, so they're going to show them to you. This is a time series with a periodic trend, right? So it's January is a bad time. You get high demand there, low demand out here in this period. It's Christmas shopping type things. Everybody's aware of that. So what's the simplest, the most naive? In fact, some of the reference material I had called it the naive approach. Is just using the last period's demand or a last period piece of data as your forecast, right? So here's your notation. The forecast for the future period, one time ahead, is just the demand for the current period. All right, well, that's easy, just a lag, right? That's okay. So yeah, what does that look like? I think I remember they do a little graph, right? How's it implemented? Like in Excel, well, here's your number of patients, here's your forecast. You're just mapping it over, right? And it's just a lag. Here was your real demand, and here's your forecast. Yeah, okay, I can do that, right? So again, these things, you think, well, these are forecasting, my goodness, but well, gee, it's a pretty easy forecast. Now, are there better ways? Well, yeah, you can immediately think of this next one. Why not, instead of just using the past demand, why don't I use the past set of demands? right? 2, 3, 4, 5. Yeah, okay, yeah, we can do that. So here, that's all this fancy equation is saying is just go back in time 1 or 0 or you have 2, 3, 4, however many you want, and just average them. Oh, yeah, I like that idea. Yeah, that's simple. Go back as far as you think is necessary. Here's an example out of the book where you're going back 2 periods or going back 4. It's not very clear to see, but yeah, so you go back 2 periods. You've got the previous 2 sessions demand average. Yeah, you come up with that. Yeah. Now you see, right? Yeah, with this data, you got a little hole up here, right? You can't make any prediction 2 periods back when you don't have any data. That's okay. That's all right. That's in the past anyway. So yeah. So is that better? Well, let's see. I think the next one is a plot. Yeah. Okay. So here you've got the 2 and 4 period. Here was your original set of data. Same patients. Here's your 2 period. Here's your 4 period. You can see the 4 period's got a little bit more lag, but maybe a little bit less susceptible to the ups and downs. What is it? What does you want? What is it that's important to you? How does it matter? And you can think about these things, like I said, in a broader context. So you don't have to just be predicting demand. One of the things that I did when I saw stuff like this was, well, why don't I take this moving average concept and think of it as a window that I'm moving along in my data set, and just treat that set of data. So I've got this window that I'm looking at. So if my window's this wide or this narrow or whatever, I'm ignoring all that data in the past. And this is where the idea I had was to take that data and look at it as a statistical distribution, and then fit that with the extreme value distribution. So I could look at the extreme values at the end. And the reason I was doing this, I was doing it actually for Y12, to try to make a prediction of when you're going to have anomalous safety issues or security issues. Because, those are kind of extreme values. You go along with 2 or 3 minor incidents a month all the time, some, slip, trip, and fall, usually something like that. But then all of a sudden we get these extreme conditions where you'll have, 3 or 4 accidents in a row. And that's, the extreme value statistics is that branch of statistics that looks at the 100-year flood, the 500-year flood. Very, very, very interesting branch of statistics. It's kind of difficult. You're trying to, you've got this general statistical distribution of, say, here's your flood depth, and you're trying to predict. You want these ones where you're way out here in the tail of the distribution. What is it going to happen every 500 years, every 1,000 years? It's very very nuanced to the shape, but it wasn't that I was doing an average. I'm just taking a window of data and now doing a statistical fit on that. So you could think broadly about this windowing approach. It doesn't have to be just an average. You could do some little fit in the window. You could use separate windows. In fact, that's one of the things I was doing. Doing some adaptive windowing where you had and you could do that on this. You could have a 4, a 2, and a 0 window, and combine those or look at those or have some logic. Which one's seeming to be using some error checking. So there's some broad things you can do with this windowing idea. So just keep that in mind as not just for an average. All right. Plus, I was amused, by the way, with the thought of that software. You think about it. If I'm looking at safety incidents and my little thing predicts that it looks like next month we're going to have a problem. So you issue some emails. Hey, our new fancy safety software says we look like we're trending towards issues next month. Be careful. Be extra vigilant or whatever. Well, then next month, if you have no incidents, you say, hey, my stuff works. Did great. And if you do, you say, hey, I told you so. You should have issued more warnings. And so it's kind of like, I think this is a win-win thing, no matter what happens. So anyway, so what else could you do? You don't have to just take this. This average where we were averaging 2 periods or 4 periods in the past. If we have a value of 1 as a multiplier by each of those, we're weighting them all equally. Well, why do that? Well, why not weight them unequally? Have a weights like in the book of 0.5 on the most recent one, 0.3 on the one 2 periods back, and 0.2 on the ones 3 periods back. You know, as you're getting older, we're assigning less weight to you, and come up with that sort of thing. So you could do that. You know, you could have an adaptive weight. You know, that could look at the weight. You could take the error between your prediction and your your previous prediction and your actual demand, take some error and adapt the weight that way or something. You know, you could think of clever things to do that might work or might not. It'd be kind of fun to play with if that was something you were looking at. So yeah, here's Flavio's Pizza. I think this is one in the book, and they're trying to develop forecasts for week 6 using a 2-period moving average and a 3-period weighting average. So period 6, they're going to use the 2-period moving average. That's just going to use these previous two. So they're saying 66.5. And they're going to use a 3-period weight where the weights are 4/10, 35, and 0.25. Now notice, you know, the weights always add up. You got to do that or you're going to be skewing things. And so there you get 63.3 pizzas. So we don't know how good they were. We're not Flavio. If they're any good or not. Okay. Well, there's other things you could do too, right? You could have exponential smoothing, where you're using both the actual demand and the forecast. And so, you know, the reason you can see why that gets that name exponential. Remember, exponentials always show up when the rate of change of something's proportional to the amount of it. Right now, you know, that's when you get the differential equation that gives you an exponential as a solution. So you're seeing my prediction is my change in the prediction is relative to my prediction. And so, but you don't care. This is the formula, right? It's a very simple formula. It's no different, or it's no harder to implement than the others, right? I take the previous period's demand, I multiply it by this alpha, which is just a constant that you select to tune your algorithm. 1 minus alpha times the previous period's prediction. That's one step harder than the naive approach, but you'll see it does quite well, actually. Let's see. There, yeah. Oh, yeah, but you do need a little guidance, right? What's that magic alpha that was in there? You know, just like the weights, kind of what was it? Well, here's your little guidance. More random, lower alpha, less random, the higher alpha. Yeah, because you can see, let's see. Yeah, a lower alpha, it becomes less dependent on the current period's demand and more dependent on your prediction. And a higher alpha, it more looks like the naive approach. So a higher alpha, it's looking more like that. You're going to be more sensitive to big variations in the previous demand, more randomness. Randomness will give you more trouble. All right, so let's see. Yeah, okay, and then I think they got, yeah, so here's an example of exponential smoothing. I've got a better example that you can look at because these are hard to read. Exponential smoothing for periods 2 through 20 with the alpha of 0.8. So they've got the demand, they've got the forecast. It's not bad though. Let's see how it's looking. So they've just implemented that equation here. Let's see. And here's the details, right? Yeah, if you want to look at each one, right? 0.8 was the alpha times the demand plus 1 minus alpha times the prediction. And you just, you know, that's why you can see with Excel, these things are great. You make it in one cell and then just drag it down. Very simple. So let's see. Yeah, so here's the plot of that one. And you can see the nice thing about it is it does a nice job of capturing this fluctuation that was, in this case, not just random. You know, this was actual, you know, a spike in demand. You improved the flavor of your Starbucks coffee, and now everybody's run to buy it, or you know, your donuts are better, or whatever it is, made you have a real spike in your demand. And then you could take this exponential one and also adjust it for a trend. So what they're saying is, oh well, you could take your prediction from the regular exponential, that's this one, and have an added adjusted piece that accounts for a trend. So you're basically having another factor, a beta factor, that's looking at the difference between your predictions and the trend factor, which is calculated from the previous trend factor. Yeah. So you could try to make a correction to the exponential for a trend, you know, where you've got a linear increase or a linear decrease. It seemed to me like the exponential smoothing worked almost as well for the data I had. So it's kind of like, this is an added piece of complexity that may not give you much better results depending on the data. So let's see. Yeah, so this is where I was going to break a second and show you that little tool I made for you to play with. So yeah, alrighty, so what did I do here? Let me look at it. I got them all. Okay, good. And I'll show you, I'll show this one first, then I'll go to the one. So what I did so you could play with things, I made you a thing over here that'll generate you some data. So what you've got is a constant term. Let's see, you got it. So your data is just a constant term plus a trend term times time, times over here, whether it's month or year or day, plus a periodic term times the sine of 2 pi f times time. So I could get some seasonal variation, plus just randomness, CR times the randomness. Random 0 to 1, right? So I was trying to throw in just a constant value, some sort of trend, up or down, periodicity, randomness. So you can play with it. These coefficients are the strength of them. So for example, in this one I don't have any periodic term. And so first thing I always do when I play with things is do something stupid like have a real simple set of data, right? Where I've got nothing but a constant term, nothing else. So my whole data is just nothing but ones. And you would hope that if your data, if your trend or your demand or whatever is nothing but ones, you would hope that all your prediction methods would come up with ones. Otherwise, I hate them. And look, oh, gee, okay. So I must have programmed things correctly. I've got ones all in there. That's pretty. Now, what have I got up here? What am I doing so that you know? Well, we just talked about, a ton of different ways to predict, right? We've talked about, I haven't talked about this yet. I'll mention it in just a second. This is the data. This is your demand. This is your supply. It's what you're trying to predict. This was that simple, the last period method. This was a 2-period weighted average. Or I'm sorry, just a 2-period average. This is a 3-period weighted average. And this is an exponential. So I was like, hey, let's do them all. Do them all on one page. That way you can look at them. And very simply, you can see I'm just doing what they did in the book. Very simple. Here's your weights on the weighted average. In fact, I took their weights. Here's the exponential. You can see how they're done. And I got a little graph over here showing how good they do. Of course, they all do great on one. Yeah. And the other thing I've got is this thing called the THEIL. That's a person's name, Thiel denominator. Let me just pull up 2 view graphs that I stole from somebody to show you what that is. Yeah, I stole them from offline, right? You're reading this stuff, and you come out, hey, this is interesting. This wasn't in the book. It's comparing your other techniques, the exponential, the moving average, to the naive approach. This is the guy that calls the naive approach is just that last period, okay? And what's it doing? Oh gosh, another equation. No. It's just taking the naive approach here and calculating the sum of the errors on your naive approach squared divided by the sum of your errors on your approach. And the reason they're squaring it is because, that way plus and minus errors don't cancel each other. You don't want that to happen. And then take the square root of it. So if you did this sum of the squares on the naive approach compared to the naive approach, you get 1, right? It's the same answer. And so if this statistic is 1, it's the naive approach. If it's less than 1, your set of errors were better, your approach is better than the naive, simple, dumb approach. If it's bigger than 1, it's worse. So it's a very simple statistic. I like it, because now it gives me a way to say, well, which one's working better under these conditions that we built. If I have lots of randomness, does this one work better? And I'll show you. It's kind of a fun thing. And this is the kind of thing I think you would want to do. Oh, well, here's the explanation of what I said. That equals to 1, the naive approach is just as good. Which, the naive approach, that was done, right? Just last periods, my guess is what I just got in demand. That's the one you're doing better. greater than 1, you're doing worse. Might as well do the naive approach. All right, so let's see. So now that we swore, and you're welcome, this has got 40 other view graphs, that somebody else's coverage of the same topic. You're welcome to dig in and look at it. So let's see. So here was my check, oh, well, you know, is it working at all? Now let's look at one where the naive approach does best. So I just sat and played with this. So here I've got a data that's got nothing but a constant term in it and a seasonal variation. Doesn't have any randomness. I made that 0. Doesn't have a trend. So basically it's a sine wave sitting at, you know, it's like the Christmas demand or something, or demand for products on at Walmart for swimming. So here you can see, in fact, I've got data going up and down. It looks like a sine wave, doesn't it? And when you look at the bottom, I've got 2 years worth of data. Here's that little statistic, right? And so, and I did a nice little if statement to tell you which one did worse. Let's see, what I should do is, be Mr. Excel rather than shrink it. Let me freeze the panes here. Freeze panes, there it is. There, that way you can see who wins, right? So yeah, so everybody's worse. In that case, everybody came out worse. Their little file statistic was greater than 1 except for this one, which was itself. So in this case, so this kind of told me with these magnitudes, what I'm playing with is these magnitudes of a constant data with just a period on there, looked like it was just, it might as well just be using the naive approach. Now why would I give you this tool and why would you do that? Because you know what your data looks like. If you've got some data, you can say, well, I didn't have any periodicity. Great, let's set a big 0 on there. I got a trend, okay. And then you can kind of play with it to see which one of these might work better, and you can play with the weights. You know, and this might change if I change these weights. You know, it might change a little bit. I didn't play with it forever. And I tell you, it will change. When you got randomness in a model and you run it, you know, and it regenerates itself each time if you don't save the data or if you don't tell it not to. So you could get one answer one time, and you know, this one's better, and then the next time it's not because the randomness messed you up. So be careful when you're doing random things. Either preserve your run that shows you doing best or not, you know, or do it 1,000 times and see, you know, if you do it 1,000 times, does this method come out best, you know, 80% of the time, or is it 50-50 or what? You know, randomness introduces a new set of requirements on things. All right, so now let's see. Here's one where the exponential won. So what happened on it? Let's see, I got a constant term, I've got a trend, I've got periodicity, and I've got some noise. So let's see, put the bottom down here if it's true. Freeze the panes again here. Should have done this all. And let's see if exponential did win most of the time. Yeah, let's see, better. Yeah, in fact, they were all better than the naive approach, right? The 2-period weighted average, everything was better, but the exponential did best. It had the lowest value of that statistic. So okay, so I think I found that it tended to do best almost under all circumstances. Here's one. I said which one because it has a lot of randomness. Okay, and so let's see. If you got down here to the bottom, we'll show you what happens with randomness. Let's see. So they're all worse there than just the plain old naive one. Now let me just enter something and get a new version. Let me just keep getting a new version because every once in a while, yeah, see, look here. Oh, wait a minute, this one got better this time. So, you know, randomness, be careful with randomness. You know, randomness is random. You know, and it can change the results. So in that case, I think that was the 2-period moving average, right? Yeah. So you see why you want a little tool like that. And over here, yeah, there's a picture of how they're doing. Well, I can scroll over and you can see which which. Yeah, so the blue is the data. This is the naive approach. The 2-period is the one that's following pretty good. The gray one, I think, yeah. The weighted. No, so anyway, all of these techniques are stuck in here. You can play with it. You can decide which one you want to use. You can build your own little data set. Make it longer than 2 months or 2 years if you wanted to, but you can compare them. And here's one I put just that trending thing. Like I said, I wasn't very interested in it yet, but I put the trender in there too. It actually did better in that case. Yeah, okay. But, so it's a good little thing to play with, and always remember to do something like that little check when you build something like this. So let's see. So that's out there, posted for you if you need it. Okay, so enough on time series. Now they're switching gears. They're still staying with time series, but they're going to use linear regression. So this is basically, in a simple nutshell, you'll fit a line to your data, right? And guess what? That's built straight into Excel. Under the data analysis little data tab, data analysis, there's a linear regression tool. It's so easy to use. Literally, you pick the data and you pick your variable levels and you push regression and it spits it out. Now, that being said, you have to think about it a little bit, but everyone can do it. Everyone can do it. And let's see. Let's let them talk about it, and then we'll look at it. So let's see. They got a little bit. Well, here. Let's see. Yeah, I should say something about here. Yeah. So you're going to fit a line, right? This is your data, and your this is your constant. There's your slope. There's your variable, your independent variable, like time or mortgage interest rates or whatever. It could be lots of variables. That's what multiple regression does. So basically, you're going to make your linear equation. I love linear equations. They're nice and easy to use. So here's the formula. Great. You don't care because you're not going to program that formula. You're going to let Excel do it, right? Or some other piece of software. And it's just straight out of statistics, really. In fact, we could derive it in the statistics class. We won't because that's a waste of your time, I think. So here, an example, for example. Clem competition clutches. It would be a car example. That's good. And you got every month, you got his demand. You can see his demand's gone up, and kind of peaked, and then it's sitting here. Yeah, it's bounced around. So he wants to use linear regression to forecast the demand for the next 3 months. Okay. So they do a great job in here doing this. They plot it for you, and then they throw out the answer here. They calculated it for you, I guess, but you don't want to do that by hand, trust me. But you get an intercept and a slope. All right, and let's see what it looks like. Yeah. So now, when you predict, right, X was your variable. X was just month. So you got your intercept, your slope, you just plug in the month, and yeah, there's your prediction. Okay. You can see how it fits. Yeah, that's not bad. Let's see, that's not what I want, but I won't show you my linear regression sheet yet, because they go on and talk a little bit more. Yeah, because I want to show you, well, I'll show you one. That's right, I got more than one. I'll show that one to you now. All right, so the first one I got for you, and these are all posted again, so if you can't see the details here, I didn't open it up yet. Chapter 9, regression. Okay, so this is the simplest one, so you can see how to use it. Alrighty. And again, this is another one of those things I played with. So I've got you some data over here. Where does the data come from? It comes from this real simple equation, right? It's I've got 3 variables. I call them A, B, and C. In their example, they just have one variable, right? X, time. I have these 3, and my equation is multiply A by that, add to it B times that, and add to it C times that. So that's a line, right? Now it's more than a line, right? You think of a line, y equals A, y equals something times X. I got 3 variables. Yeah, that's all right. 3 lines combined together, make it a plane in hyperspace. So 2 dimensions, we could make a big plane. 3 dimensions, but anyway, it is definitely a linear function, right? I don't have anybody's the column A is not squared, B is not squared, or multiply by each other, no logs in there, no signs. It's a line. All right. So the way you can do linear regression, I'll just do one for you, providing this works good. Yes. So let's see. Data analysis. Remember, you have to add it in. It takes the extra step. Down here at the bottom, regression. Okay. Input the Y range. And I always like to select the name That way when the name comes out, it says Y and doesn't say some random thing. Okay, input the X. If you just want it to be a function of A, just grab that column. If you want it to be a function of all three of them, which would be nice, let's do that. Okay, and then do you want it to tell you what the name of them was? Yeah, I do. You want some statistics? Yeah, I do, even though we'll talk about that next class. And I like it on a new worksheet, but you can put it right here on this sheet if you want. We'll just put it on a new worksheet. Okay, so what did it do? Well, it threw out a bunch of statistics. One in particular, the R squared, tells you how good the fit was. 1 means good, 0 means really bad. Some more statistics. This will all be very clear and completely understandable after statistics class. Every bit of it. And simple. And then what do you get? Well, here's the coefficient on A, B, and C. If you recall what I had, right? I had 1, 0, and 0.1. Oh, okay. 1, 0, that's 0, right? 0.1, and the intercept is 0. We didn't have any constant term on there. So, boy, that wasn't very hard to get a nice linear model of 3 variables. You know, I think we can all use that, and with confidence even, especially after the statistics class, and you'll understand all of that. Yeah, in fact, it was very good. It got it exactly right, didn't it? And that's as good as you're going to get a 0 on you know, with numerical calculations on a computer. Got them exact. Why was it so good? You know, this is data, right? Well, I don't have any error in my data, did I? I calculated, I had A, B, and C, and I calculated exactly. You know, perfect. I had perfect data. May not always have that, you know, and I'll show you that. I'll show you that. But just for fun, you know, here's one where I had 1, 1, 1 as my coefficients. Well, son of a gun, look what it showed me. Here's one where I had 1, 0, 1. That was one we were looking at. The one we just did. Here's 1, 0, point 1. No, this is one we just did. 1, 0, point 1. So you can see this works. It's very simple to use. Now you sit around and you say something to me. Yeah. You say, well, I really, really like that, but I got other things going on. And I might have, in fact, I do have this. You know, what if I have something like this? In fact, I had this week. So what that was, I was trying to design a transformer this week. And this is the power loss per kilogram of the transformer. This is just a coefficient. This is the frequency. And this is the flux. That's not very linear, is it? That doesn't look linear at all. But I'd like to fit that. I'd like to use this dumb tool. Well, don't forget your math, right? Two steps at once there, if that knows you. Shoot back again, huh? Now that's pretty linear, right? If I take my data, so now if instead of throwing these things in the columns, if I throw the log of Q in the columns, and the log of F, and the log of B in the columns, then my constant term is going to spit that out, and that, and that. Well, that's pretty linear, you know. That's pretty easy to take a complex thing that was not linear and turn it into a linear and use linear regression. That's not hard. That was 2 steps. I can usually do that. Well, let's see. Does it work? Well, there's your equation. Here's the frequency, and let's see. I put in a K and an M and an N that I got from a manufacturer. Well, I'll make up some real data. Why don't we do that? So here's my core loss right there. And let's see. I got some frequencies, just made a range of frequencies and a range of fluxes. took the log of this, and took the log of the frequency and the log of the flux. Let's use this data right here and see if it predicts. Because if it predicts, if it can give me these numbers right back, it's working, right? I'll put in that as my data, and if it spits it right back out, I got a good technique. Well, look what it did. Let's see. Forget about this one for a minute. I said that was M, didn't I? And that was N. You remember what they were? They were 1.68, 1.8. Worked great. Worked great. And what's this? Why does that look strange? Well, remember, it's the log of K. So I got to take the 10 to the power of that. If you take 10 to the power of that, what do you get? Oh, okay. So I'm confident in my technique, confident in my mathematics. It's very easy. Now, again, I would ask you, why is this so dang good? It's not got any mistakes, right? 1.68, I love this technique. Well, I didn't have any error in my data, right? So what if I go over here, just for fun, and goof up my data just a little bit, add some randomness to it. For example, I was taking this power per kilogram with an instrument. Had some uncertainty. I couldn't read the dial. My glasses are crappy. Whatever, I got some experimental error. So I added a little random error on here, and let's treat this data. Well, let's see what we get there. Okay. So it's not quite as good, right? Some mistakes. Well, I hope so. You had some error in the data, but this technique is still working, right? And I could still use it. If I had more data points, these would be better. If I had a better instrument, my RAND wasn't so big. I just made one up and threw it in there. Then these would be closer and better. Because clearly, if it was zero, no error, it was exactly right. So you see how you can play with these kind of things. They're broader than just, and I'm not saying you're going to be predicting core loss. No, probably not. But this could have been your model for some weird demand, right? Some odd function of time and people's income or something weird. You just think broadly. Think broadly. You don't have to just restrict yourself to y equals mx plus b. It's a lot broader than that. You already saw three lines, three functions. Here's a nonlinear exponential thing. And again, you don't have to memorize this. It's all it's all online, or you can come to me and ask if you've got something weird that you want to use. But it's nice to put it in your head and say, yeah, it is there. You can see how this kind of stuff is fun. So let's see. So back to the view graphs. We're done with the sidebar there, right? Oh, yeah, they're trying to motivate you. Why would you have seasonal variation? Yeah, we know that. Yeah, gas always goes up every time I get ready to go on vacation. Fruitcake has no demand. I used to play football for the Oak Ridge Boys Club when I was a little kid, and we used to have to sell fruitcakes every winter. And the reason we did was so we could fund our trip down to Disney World. And so, and I've never had anything so hard to sell as those fruitcakes, and it used to kill me. Work 2 days worth of Saturdays to sell 3 fruitcakes. It was easier to sell the tickets to the football classic, which was a bunch of little 12-year-old boys playing football. And the reason that was easy to sell is because the tickets were $1, and no one would buy the tickets, not a single person. But you could always say, well, would you like to give just a tiny donation to the Boys Club? So they'd all reach in their pocket and give you a quarter or nickel or dime. And after you got 50 people giving you a quarter, nickel, dime, you just bought your own tickets. That's the difference. And so that was easy, but not the fruitcakes. Not that fruitcakes at all. They were hard. All right, so how can you adjust for season? Well, you can take your predicted demand and your forecast and just form a ratio, right? If I've got some sort of seasonal demand that's changing and I got some forecast and I've missed, why don't I just take a ratio or an error or something like that and multiply by the ratio to fix it up? So if I had several periods, I could also average this ratio. I could have a ratio for January, February, March, April, May that I've got from the last 5 years. And my prediction model always misses by, it's always 80% of what it should be, or I'm always 20% high. You can have it's an error correction term is all it is. So that's what they're talking about here. So for example, they've got a model, they used a linear regression model, right? So they got a line, but you really had, so you had a trend, that was good, but you also had this periodicity. That's what we have with our little sine wave term. So you look at these errors and you come up with a you know, a percent multiplier to fix that up. So that's what they're doing here. Let's see, how are they doing that? Yeah, so they're taking, here was your demand, here was your forecast. Oh, you were way off here, way off here, way off, you know, way high here, way low here. Yeah, because it's giant sine waves stuck on top of this line, and you're trying to predict it with a line. So you had a 50% error negative there, 100% error positive there. So you just take this and use a multiplier, fix it up. Because basically what you're saying is, I'm aware that my linear model is off due to periodicity, and it's off positive here, negative there. Yeah, so, oh, what's that? Yeah, the 2 years worth of data, right? This is the only mistake on this view graph. This is January 2016 and January 2017, and then the next view graph, they're going to do your calculations. All of a sudden, they magically change years. So don't worry about that. That's 2016, 2017, or the best data was 2012, 2013, whichever one you want to switch. So see, they're just taking the ratio. And so your multiplier is that for that year. Your multiplier was that for that year. Let's average them. There's our multiplier. So for the future, we'll just multiply by that number until we make a new average, right? 3 averages or 2 averages, something like that. Just a simple correction. So here, yeah, so here's your 2 multipliers by the ratio of your mistake. You average them, so your adjusted demand is just multiplied by that. Makes sense. You could come up with other ways to correct it. I mean, you could take your, you know, fit your sine wave to it, right? And then add that and have a frequency on it if you wanted to. There's no reason you couldn't do those kind of things. Oh yeah, so there's your model and there's your result. Looks good, looks good. Nice job. So now we kind of switch gear just a tiny bit and try to say, you know, everything we've looked at is time, right? Seasonal, periodicity, time. Don't get stuck on time, right? You might have a causal relationship. Maybe it's dollars. Maybe it's mortgage refinancing rate. Yeah, maybe it's, you know, the amount of something else that's your function. And as well as time. You know, we just saw that linear regression I did with A, B, and C. One could be time, one could be, you know, mortgage rates, one could be